Okay, then let's continue part 2 of mechanical properties of fluids. Part 2 of mechanical properties of fluids. Let's go. We have completed atmospheric pressure and gauge pressure yesterday. So let's start with this example, which I didn't do yesterday. Example 10.3, the density of the atmosphere at sea level is 1.29 kg per meter cube. Okay, assume that it does not change with altitude, then how high would the atmosphere extend? They gave the density of the atmosphere that is at sea level. We know the atmospheric pressure. We know the formula, which is rho gh. Rho gh, which is equals to atmospheric pressure. So G value we know, pressure value we know. They gave the density value, that is rho. So the only thing left out is h. We can find out by substituting the formula, and rho gh, which through which we will substitute the values, we will get h, which is approximately equal to 8 kilometers. In reality, the density of air decreases with height, so does the value of G. The atmospheric cover extends with decreasing pressure over 100 kilometers. We should also note that sea level atmospheric pressure is not always 760 mm of Hg. A drop in the Hg level by 10 mm or more is a sign of an approaching storm. Okay, let's read that to understand what they said. In reality, if we see, because the value of G decreases as we increase in height, the density of the air also decreases as the height increases. With decreasing pressure, and the atmosphere actually extends with decreasing pressure over 100 kilometers. What we calculated is 8 kilometers for density, which is with constant density, but without constant density it will extend over 100 kilometers. We should also note that sea level atmosphere, the atmospheric pressure at sea level is not always 760 millimeter of Hg. And if we see a drop in the pressure by 10 mm or more of Hg, then we can assume that there is a storm approaching. It's a sign of a storm approaching. Now example 10.4, at a depth of 1000 meter in an ocean, if we assume at a depth of 1000 meter in an ocean, what is the absolute pressure? What is the gauge pressure? Find the force acting on the window of area 20 centimeter 20 centimeter 20 x 20 centimeter square of a submarine at this depth, the interior of which is maintained at sea level atmospheric pressure. The density of seawater is 1.03 into 10 power 3 kg per meter cube, and G, which is equal to 10 meter per second square. Okay, they gave the height, that is 1000 meter per second, or depth 1000 meter. What is absolute pressure? Basically just pressure. We find P value from P, which is equals to PA plus rho GH. Gauge pressure is P minus PA, which is rho GH. Now if we find out pressure, then pressure, which is equals to force by area, by multiplying area with pressure we will get force. Okay, let's see. At 1000 meter, and rho is equals to 1.03 into 10 power 3. Substituting this formula, we will get P, which is equals to 104 atm, where 1 atm, which is roughly equal to 1.01 into 10 power 5 Pascal. Here it is 104 atm. Gauge pressure, which is equals to P minus PA, which is equals to rho GH, that is approximately equal to 103 atm. The pressure outside the submarine, which is equals to P minus PA plus rho GH, and the pressure inside is the atmospheric pressure, and the net pressure acting on the window is gauge pressure, where gauge pressure, which is equals to Pg, which is equals to rho GH. Basically, since there is a sea level pressure inside the vacuum, I mean inside the submarine, which is pushing against the walls of the submarine, the pressure acting on the submarine due to the water will reduce, they will get cancelled out. That is only the atmospheric pressure. Pressure equal to the pressure inside the submarine will get cancelled out from the pressure, total pressure that is due to the seawater, by which we will get the only pressure acting on the submarine, which is equals to Pg, which is equals to rho GH. And since area, which is equals to 0.04 meters square, the force acting on it is which is equals to Pg times A, which we will get as 4.12 into 10 power 5 Newton. So for a submarine designed to operate at such depths, the walls of the submarine must at least withstand this much pressure for the submarine to not collapse. Now let's go to hydraulic machines. Let us now consider what happens when we change the pressure on a fluid contained in a vessel. Consider a horizontal cylinder with a piston and 3 vertical tubes at different points. Okay, we consider what happens when we change pressure on a fluid contained in a vessel. Okay, there is fluid contained in a vessel. Now what will happen if we change the pressure on a fluid contained in, okay, we change the pressure, we apply a new pressure on this fluid, what will happen then? If we consider a horizontal cylinder, if this is a horizontal cylinder and we consider 3 vessels of different shapes, the pressure in the horizontal cylinder is indicated by the height of the liquid column in the vertical tubes. It is necessary the same in all. We push the piston, the fluid level rises in all the tubes, again reaching the same level in each of them. Okay, why that happens? Basically, if we take a something like this apparatus here, this is the long tube, this is blocked end, there are 3 vessels connected in such a way, although they contain different, although they are of different shapes, and might also contain different volumes, because pressure depends only on density G and H. The pressure induced here, according to Pascal's law, the pressure is transmitted throughout in a in a fluid in rest. If we apply pressure at one point, this pressure is transmitted in all points of the liquid, that is Pascal's law. So when we apply pressure here, it will be transferred here, here and here, and this pressure, which is equals to, let's assume it's some pressure, and because this water is not falling down, that means the pressure must be equal to rho GH, and it depends on density of liquid, which is same in all 3 cases, gravity, which is because they are at same height, all of the gravity is also same, acceleration due to gravity has very minimal change, and because of that, because the pressure applied for all of them is same, rho is same, G is same, Because of that, P by rho GH, which is equal to H, because P is constant for all of them, rho is constant for all of them, and G is also constant for all of them. Height is also constant for all of them. Whenever external pressure is applied on any part of fluid in a vessel, it is equally transmitted in all directions. And actually, if we do not know the pressure, if we do not know or do not know like if the pressure is same or not, we can identify it by observing uh, this apparatus here. Because height is same for all of them, we can consider height to be constant, and G and rho are obviously constant. Because of that, that must mean that pressure is equal for all of them. This indicates that when the pressure on the cylinder was increased, it was distributed uniformly throughout. We can say whenever an external pressure is applied on any part of a fluid contained in a vessel, it is transmitted undiminished and equally in all directions. This is another form of Pascal's law, and it has many applications in daily life. A number of devices such as hydraulic lift and hydraulic brakes are based on Pascal's law. In these devices, the fluids are used for transmitting pressure. In hydraulic lift, as shown in figure 10.6b, two pistons are separated by space filled with a liquid. A piston of small cross-section area A1 is used to exert a force F1 directly on the liquid. The pressure P, which is equals to F1 by A1, is transmitted throughout the liquid to larger cylinder attached with a larger piston of area A2, which results in an upward force P into A2. Therefore, the piston is capable of supporting a large force, large weight of say a car or a truck. Basically, here if we see this is fluid at rest, we know that if we apply pressure here, it will be transmitted in all points of the fluid. And if we take two pistons here, we know that pressure at point 1, this surface here, and this surface will be equal because of Pascal's law. Force at 1, pressure which is equal to force by area, is equals to F2 by A2. If we consider that A2 is larger than A1, A2 is larger than A1, that means F1, the force at this point, F2, yes, F2 is also greater than F1. F2 is also greater than F1 because when if A2 is greater than A1, that means the area is greater than A1 and the force applied will be more than the first area. Because of that, even when we apply a less force in this piston, a larger force is applied in this piston. Because of that, with less force only, you can lift cars and trucks. Application of hydraulic lift. Placed on the platform, F2 is equals to PA2, F1 by A2 by A1. By changing the force at A1, the platform can be moved up or down, thus the applied force has been increased by a factor A2 by A1, and this factor is the mechanical advantage of this device. The example below clarifies it. Schematic diagram illustrating the principle behind a hydraulic lift, a device used to lift heavy loads. Let's see that Archimedes principle once. It is given here. Fluid appears to provide partial support to the object placed in it, called buoyancy. When a body is wholly or partially immersed in a fluid, it is at rest. The fluid exerts a pressure on the surface of the body in contact with the fluid. The pressure is greater on lower surfaces of the body than upper surfaces, As pressure in a fluid increases with depth, the resultant of all forces an upward force called buoyant force. A cylinder is immersed in the fluid, the upward force on the bottom of the body is more than the downward force on its top. The fluid exerts a resultant upward force or buoyant force on the body equal to P2 minus P1 into A. We have seen in equation 10.4 that P2 minus PA, which is equals to rho GHA, that is the liquid element, where HA is the volume of the solid and rho HA is the weight of the equivalent volume of this fluid. Thus, the upward force exerted is equal to the weight of the displaced fluid. Results holds true for irrespective of the shape of the object, and here cylindrical object is considered only for convenience. This is Archimedes principle. For totally immersed objects, the volume of the fluid dispersed by the object is equal to its own volume. If the density of the immersed object is more than that of the fluid, the object will sink as the weight of the body is more than the upward thrust. If the density of the object is less than that of the fluid, it floats in the fluid partially submerged. To calculate the volume submerged, suppose the total volume of the object is VA or Vs, and a part Vp of it is submerged in the fluid, then the upward force, which is weight of the displaced fluid, which is rho FGVP, which must be equal to the weight of the body. Rho S is the weight of the body. I mean, it's a rho SVS is the weight of the submerged portion of the body, and rho FGVP is the weight of the displaced fluid. Or simply shifting it, we will get this equation. The apparent weight of the floating body is 0. The principle can be summarized as the loss of weight of a body submerged partially or fully in a fluid is equal to the weight of the fluid displaced. Let's see an example. Two syringes of different cross section without needles filled with water are connected with a tightly fitted rubber tube filled with water. Diameters of the smaller pistons and larger piston are centimeter or 1 centimeter and 3 centimeter respectively. Find the force exerted on the larger piston when a force of 10 Newton is applied to the smaller piston. The smaller piston is pushed in through 6 centimeter. How much does the larger piston move out? Okay, they are saying that there are two syringes and they are of different cross sections. They do not have needles, and they are connected with a tightly fitted rubber tube, and this rubber tube has water. Diameters of the smaller piston and larger pistons are 1 and 3 centimeters respectively. First thing, we need to find the force on the larger piston when a force of 10 Newton is applied on the smaller piston. Basically, we find area, then pressure on the two pistons is same. Pressure, which is equal to force into area, force by area, not force into area, force by area, which will be same for both the pistons. So when we equate F1 by A1, which is equals to F2 by A2, where we know the area of the second syringe, we know the area of the first syringe, and force applied on the first syringe, So we can find out the only unknown, that is F2, the force on the second syringe. Since pressure is transmitted undiminished to the fluid, F2, A2 by A1, we will get it as 90 newtons, a 9 times increase in pressure, I mean force. Water is considered to be perfectly incompressible. Volume covered by the movement of smaller piston inwards is equal to volume moved outwards due to larger piston. Because water is considered to be incompressible, volume covered by the movement of smaller piston is equal to volume moved out due to the larger piston. That means length, which is given, area which we know, the only unknown is L2. Substitute it, we will get it as 0.67 centimeter. The atmospheric pressure is common to both piston and has been ignored. Now let's go to the next example. In a car lift, compressed air exerts a force F1 on a small piston having a radius of 5 cm. This pressure is transmitted to a second piston of radius 15 cm. The mass of the car to be lifted is 1350 kg. Calculate F1. What is the pressure necessary to accomplish this task? Okay, this is, we are trying to lift a car. In a car lift, there is compressed air. It is exerting force F1 on a small piston having a radius of 5 cm. This is transmitted to second piston of radius 15 cm. If mass of car is to be lifted is 1350 kg, now we need to calculate F1. How much force we need to apply to lift the car. Same formula, pressure will remain same in both the surfaces or both the on the both the pistons. Because of that, F1 by A1, which is equals to F2 by A2. We know area of both the pistons because radius is given, pi r square is area, and we know the second force which we need to which has required to lift the car, which is the weight of the car, basically 13.1350 into 9.8, which will get the total force required to lift that car. Now using that equation, since pressure is transmitted undiminished throughout the fluid, F1, which is equals to A1 by A2, and times F2, which is equals to 1470 newtons, 1.5 into 10 power 3 newtons. Which is although less compared to the weight of the car, which will come out to be around 1300 into 10, or basically 1.3 into 10 power 4 newtons. The weight of the car is around 1.3 into 10 power 4 newtons, but the force we need to apply on the first piston to lift the whole car is only 1.5 into 10 power 3 newtons. The air pressure that will produce this force is pressure, which is equals to F1 by A1 which the first surface force, which is equal to this much force, should be provided, and area is for the first piston, it is almost double the atmospheric pressure. Hydraulic brakes in automobiles also work on same principle. When we apply little force on the pedal with our foot, the master piston moves inside the master cylinder, and the pressure caused is transmitted through the brake to act on a piston of a larger area. A large force acts on the piston and is pushed down, expanding the brake shoes against the brake lining. In this way, a small force on the pedal produces a large retarding force on the wheel. An important advantage of the system is that the pressure set up by the pressing the pedal is transmitted equally to all cylinders attached to the four wheels, so that braking effort is equal on all wheels. There is a small note given about Archimedes here. Archimedes 287 to 212 BC. Archimedes was a Greek philosopher, mathematician, scientist, and engineer. He invented the catapult and devised a system of pulleys and levers to handle the heavy loads. The king of his native city, Syracuse, Hero II, asked him to determine if his gold crown was alloyed with some cheaper metal, such as silver, without damaging the crown. The partial loss of water he experienced while lying in his bathtub suggested a solution to him. According to legend, he ran naked through the streets of Syracuse, exclaiming, Eureka, Eureka, which means, I have found it, I have found it. Okay, that's about him. Now let's go to the next main topic, that is streamline flow. Streamline flow, so far we have studied fluids at rest. Okay, the study of fluids in motion is known as fluid dynamics. When a water tap is turned on slowly, the water flow is smooth initially but loses its smoothness when the speed of outflow is increased. In study of the motion of fluids, we focus our attention what is happening on various fluid particles at a particular point in space at a particular time. The flow of the fluid is said to be steady at any point. The velocity of each passing fluid particle remains constant in time. This does not mean that the velocity at different points in space is same. The velocity of particle may change as it moves from one point to other. That is, at some other point, the particle may have a different velocity, but every particle which passes the second point behaves exactly as the previous particle that has passed the point. Each particle follows a smooth path, and the paths of the particles do not cross each other. Basically, what they say is the motion of the study of motion of particles is known as fluid dynamics. Okay, that is what they said first. Now, what is steady flow? What is a steady flow of water? Normally, we define steady flow of water as the steady flow of water is when in the flow of water, if all particles of water at a certain point in space have equal or same velocity, Meaning, if this is the flow of water, if this is the flow of water, then at this plane or point here, at this plane or space here, all the particles of water should have a certain velocity, certain and same velocity. Meaning, if one particle in this plane has a velocity of 1 meter per second, then the second particle which comes from here will also have the same velocity. Meaning, in this at this point, all the new particles coming to this point should have the same velocity, or in this point or any kind of point, all the particles coming to those points should have the same velocity as the particles that pass through those points. That is what we mean by a steady flow. And the particles should not cross over each other. Like if a particle is going like this, another particle should not come and intersect like this. That should not happen in a steady flow. That is what they mean by a steady flow. The paths of the each particle flows a smooth path, and the paths of the particles do not cross each other. That's what they mean. The meaning of streamlines: a typical trajectory of a fluid particle. This is the typical trajectory of a fluid particle. This is the typical trajectory of a fluid particle. It goes like this, and like this. A region of a streamline flow where particles, these are three surfaces, the particles go like this. Anyways, the path taken by a fluid particle under a steady flow is a streamline. What is a streamline? A streamline, we understood what a steady flow of water is. Now, what is a streamline? A streamline is a streamline is the path taken by a steady flow of water, or the path taken by a fluid particle which is under a steady flow, which is under a constant velocity at every specific point. That is a streamline. It is defined as a curve whose tangent at any point is the direction of the fluid velocity at that point. Okay, let's take a 2-minute break. Okay, then let's continue. The path taken by a fluid particle under a steady flow is known as a streamline. It is defined as a curve. What is a streamline? Is the path taken by a fluid particle under a steady flow. A steady flow is when a particle is having constant velocity at the same point. Every particle of velocity passing through a point is having a same velocity. That is called as a steady flow, and this fluid particle under a steady flow is called a streamline. It is defined as a curve whose tangent at any point is in the direction of the fluid velocity at that point. Let's read that again. It is defined, the streamline is defined as a curve whose tangent at any point is in the direction of the fluid velocity at that point. Basically, here if we say they showed the streamline here, the meaning of streamline, a typical trajectory of a fluid particle. Here if we see, this is the path of the fluid particle. If this is the path of the fluid particle, then here we take tangents like this. At this particular point, this is the direction of the streamline. At this particular point, this is the direction of the streamline. And at this particular point, this is the direction of the streamline. Now then, let's continue. It is defined as a curve whose tangent at any point is in the direction of the fluid velocity at that point. Consider the path of a particle as shown in figure 10.7a. The curve describes how a fluid particle moves with time. This shows how a fluid particle moves with time. The curve PQ is like a permanent map of fluid flow, indicating how the fluid streams. No two streamlines can cross, for if they do, an oncoming fluid particle can go either way, either one way or the other, and the flow would not be steady. For a steady flow, a streamline is defined by a steady flow of particles at certain point. No, the it is defined, a streamline is defined as the path followed by a steady flow of particles. So when the two streamlines do get crossed, then it won't be a steady flow anymore, because at steady flow the particles do not cross, as if they do cross at a certain point, there will be two directions of velocity, and that is not possible. The velocity must be constant at a certain point for all particles that pass through. It cannot be two different points, cannot be two different directions. Hence, in steady flow, the map of flow is stationary in time. How do we draw closely spaced streamlines? If we intend to show streamline of every flowing particle, we would end up with a continuum of lines. Consider planes perpendicular to the direction of fluid flow. Example, at 3 points PRQ in figures 10.7b. Okay, basically, if we want to show streamline of every particle, there will be many lines and it's hard to show. It's very arduous process. So because of that, what we do is, like in case of diagram 10.7b here, this is the streamline flow. Then we take three lines PQ through R. We should end up with, okay, consider planes perpendicular to the direction of the fluid flow. At 3 points P, R, and Q, the plane pieces are so chosen that their boundaries be determined by the same set of streamlines. This means that the number of fluid particles crossing the surfaces are indicated at PRQ is the same. Meaning, what they mean is that if we take three pieces of planes here, this plane and this plane and this plane, according to the diagram, what this means is the number of particles passing through P will be equal to the number of particles passing through R, and also equal to the number of particles passing through Q. It's kind of setting a boundary. If area of cross section at these points are AP, AR and AQ, the speeds of the fluid particles are Vp, Vr and Vq. Mass of fluid delta Mp crossing at AP with small interval of time delta T. What we are considering is mass of fluid crossing at delta, I mean AP, at a small interval of time, that is delta T, that is rho AV by delta T. We know that mass times, I mean density times volume is mass, and volume, which is area into velocity, I mean area into distance, where velocity is distance by time, rho into area into x by t into delta T. These get cancelled. We will get rho A times x is volume. So this will become, totally will become the mass of the fluid. Similarly, mass of fluid delta M flowing or crossing at the AR in a small interval of time, delta T is PR, AR, VR, delta T, and mass of fluid delta MQ is that the mass of fluid flowing out equals the mass of fluid flowing in, meaning mass will be constant. Mass will be constant at all places where we can equate them all. For flow of incompressible fluids, density will be same and equation will reduce. So since time is same, we will get AP Vp, which is equals to AR VR, which is equals to AQ VQ, where A times V, area times velocity, which is equals to constant, which is called the equation of continuity, and it is a statement of conservation of mass in flow of incompressible fluids in general, AV, which is equals to constant. Okay, it is kind of okay to derive. Let's try deriving it then. Mechanical properties of fluids. This is the fluid. We are kind of deriving the equation of continuity. Basically, let's assume there is a pipe. If there is water steady flow here, this is the cross section of a pipe. Let's assume the diagram will not be perfect because there will be some errors here. This is a kind of pipe, let's assume, and these are the areas of the pipe. And if we name it as area AA, surface A, surface B, and surface C. This will be area of AA, AB, and AC. If we consider mass of the particles for a steady flow where water will be flowing like this, for a steady flow at this particular plane, the particles at certain point should have equal velocity, but that is not needed here. For a steady flow, only for a steady flow where there is no crossing between the streamlines, here in that case, if we take for example the surface B, the mass of particles, the mass of the fluid passing through this area is how much. We need to find that out. Mass of particles, I mean mass of the liquid passing through B per time T. Mass, which is equals to rho times V. So it will be mass of particles, mass delta times T, which is equals to rho V delta T. No, wait, there is no need for this right now. There is no need for delta T. Mass, which is equals to rho V. Now volume we can write as area of the cross section B, which we are considering right now. Rho B, wait a second. Okay, for that surface, and let's take it as it's moving forward uh, with distance, it moved forward a distance of x. This will still remain mass. Now again, let's divide both sides by time. Delta t is equals to rho a b by x by delta t, where this is velocity. So mass by delta t, which is equals to rho a b v of the particles, v at b. Even for a streamline flow, it is not required that the velocity is always equal. This is velocity, the above one is volume, m by delta t, which is equals to rho a b v velocity v at that particular plane, mass, pure mass, which is equals to this value, and mass of these particles will not change. It will always remain constant as conservation of mass. So, and this is mass at surface B, which we do not need to denote it like this, but let's just denote it for now. And mass at surface A, which is equals to, for rho A VA delta T C, we will get these equations. Due to conservation of mass, MA, which is equals to MB, which is equals to MC, and for incompressible liquids or fluids, for incompressible liquids or incompressible fluids, for incompressible fluids, rho, which will not change. Now equate all of them, we will get, using this equation, equate all of them. We will get rho A, which is equals to A VA delta T rho C AC, which is equals to that much, and rho B area B, velocity B, and time T. These based on this condition, they will get cancelled. Now time will remain constant. Time will get cancelled. We will get A velocity A, which is equals to area at B, velocity B is equals to area at C and velocity at C. This is the equation of continuity. Equation of continuity. Now we can also use mass big for for like fluids which are not incompressible. Mass is constant, but we may also try with density for incompressible fluids. For a we can equate density, but we will get the same result. This is the derivation for equation of continuity, and based on this we can say that area times velocity for a steady flow, which is always equals to constant. Let's go back to textbook. AV gives the volume of flux or flow rate and remains constant throughout the pipe of flow. Thus, at narrower portions where the streamlines are closely packed, velocity increases and vice versa. What AV gives is the volume flux or flow rate. AV is giving the flow rate of the streamline. It is constant throughout the pipe, that is of flow, and we can observe that at narrower portions where streamlines are closely packed, velocity increases and vice versa. We can see the relation as well here. Here if we see, we saw that AV is constant, so that means if constant AV which is equals to K, that means A which is equals to K by V, meaning area which is inversely proportional to velocity. Higher the velocity, lower the area, or another way of saying it is velocity which is K by A, or velocity is inversely proportional to area. As area increases, velocity decreases. As area decreases, velocity increases. For smaller areas, velocity is more. For larger areas, velocity is less, based on this relation. Let's go back. AV gives the volume flux or flow rate and remains constant throughout pipe of flow. Thus, in narrower portions where streamlines are closely spaced, velocity increases and vice versa. From it is clear that AR, which is greater than AQ, or VR, which is smaller than VQ. The fluid is accelerated while passed from R to Q. This is associated with a change in pressure in fluid flow in horizontal pipes. Steady flow is achieved at low speeds beyond a limiting value called critical speed. This flow loses steadiness and becomes turbulent. One sees when a fast flowing stream counters rocks, the small foamy whirlpool like regions called whitewater rapids are formed. Okay, let's see what they said here. Steady flow is achieved. This steady flow, what we see, is achieved only at low flow speeds. When the velocity of the water is less, only then we can see it. and beyond a certain limiting value called the critical speed of the flow. Beyond this critical speed, the flow will lose its steadiness and it will become a turbulent stream. Opposite of steady is turbulent, where at each point the velocity of particle will not remain constant. One sees this like this turbulent flow when a fast flowing stream encounters rocks and small foamy whirlpool like regions called whitewater rapids are formed. Figure 10.8 displays streamlines for some typical flows. For example, 10.8a describes a laminar flow where the velocities are different at different points in the fluids, may have different magnitudes, but their directions are parallel. And B gives a sketch of a turbulent flow. The first diagram shows this is called a laminar flow where all the particles, this is a steady flow, it's a steady flow, but at different points the magnitudes of velocity will change. The only condition for steady flow is that at a certain point in space, at that point all the particles that come to that point should have same velocity, same direction. That is the only requirement for steady flow. These particles which are flowing in the streamline, at this point the velocity may be in this direction or any kind of direction. Here as well it may be any kind of direction, but all the particles that come to that specific point should have the same direction. And a laminar flow is a specific condition of a steady flow where the all the particles, or I mean all the particles will have same direction. The magnitudes of velocity may be different, but all the velocity directions will be same. They will be parallel to each other. And this shows hitting a rock situation where it shows a turbulent flow where this region doesn't have equal velocity as equal velocities at equal time. Some streamlines for fluid flow, a jet of air striking a flat plate placed perpendicular to it. This is an example of a turbulent flow. Okay, leaving that, we will come to the next main topic, that is Bernoulli's principle. Fluid flow is a complex phenomenon, but we can obtain some useful properties for study of stream flow, steady or streamline flows using the conservation of energy. Okay, this fluid flow we know is a complex phenomenon involving many particles, many individual atoms which have different velocities at different times. It's very complex. We can obtain some useful properties for steady flow or streamlined flows using conservation of energy, because energy can neither be destroyed can or be nor be created, can neither be created nor be destroyed. There is a conservation of energy. Based on that, taking energy to be constant, we can get some useful properties of this streamline or steady flow. If we consider a fluid moving in a pipe way of varying cross-sectional area, let the pipe be at varying heights as shown in figure 10.9. This is a figure here. The flow of an ideal fluid in a pipe of varying cross-section. The fluid in a sectional length V1 delta T moves to section of length V2 delta T in time delta T. Okay, this is basically a pipe. A pipe is basically in this kind of varying length. At the initial position the height is h1, and the second position the height is h2. Now consider a fluid moving in that kind of pipe having a varying cross sectional area. Cross sectional area is also not same, having a varying cross sectional area, and it is at varying heights. We now suppose that an incompressible fluid is flowing through the pipe in a steady flow. It's kind of a water is incompressible almost, so it's that kind of fluid. Its velocity must change as a consequence of equation of continuity. Okay, because we know consequence of equation of continuity, meaning as area increasing velocity decreases, as area decreases velocity increases, and we saw that this pipe has a varying cross section. So at higher area the velocity will be less, at lower area velocity will be high. A force is required to produce this acceleration, which is caused by the fluid surrounding it. The pressure must be different in different regions. Why this? We know that for a particle to accelerate, or for a particle to increase in velocity, there must be an acceleration, and for an acceleration to be provided there must be a force. How is this force provided? This force must be due to the pressure difference. Pressure due to the fluid particles. At there must be a pressure difference between the two areas. That is the reason why there might be an acceleration. And basically, if we consume this as a smaller area and this as a larger area, there must be a decrease in velocity at larger area and increasing velocity at the smaller area. So as water or fluid enters larger area to smaller area, force is applied to increase the acceleration. That means the pressure at the larger area must reduce to accommodate this acceleration. Bernoulli's equation is a general expression that relates the pressure difference between 2 points in a pipe to both velocity change, kinetic energy change, and elevation height changes, potential energy change. The Swiss physicist Daniel Bernoulli developed this relation in 1738. If we consider the flow at two regions, one that is at BC and two that is at DE, let's see the diagram. This is BC and DE, they have different areas. Okay, consider the fluid initially lying between B and D in an infinitesimal time interval delta t. The fluid would have moved. Suppose V1 is the speed at BD, B and V2 at D, and fluid initially at B has moved a distance of V1 delta t to C. V1 delta t is small enough to assume constant cross section along BC. The same interval delta t, the fluid initially at D moves to E, distance equal to V2 delta t. Pressures P1 and P2 act as shown on plane faces of areas A1 and A2, binding the two regions. The work done on the fluid at left BC is W1, work done which is equals to force times perpendicular distance, and force which is equals to pressure into area, distance which we got it as V1 delta t. Since area times distance is volume, we can write it as P1A1, which is P1A1V1 delta T, which is equals to P1 delta V. So the same volume delta V passes through both the regions. From the equation of continuity, the work done by the fluid at the other end, dE, is W2, which is P2A2V2 delta T, which is equals to P2 delta V. Or the work done on the fluid is minus P2 delta V. So the total work done on the fluid is W1 minus W2, which is equals to P1 minus P2 delta V. Part of this work get converted into kinetic energy of the fluid, and part goes into changing the gravitational potential energy. If density of the fluid is rho and delta m, which is equals to delta rho a1 v1 delta t, which is again equal to rho delta v is the mass passing through the pipe in time delta t, then changes in gravitational potential energy is delta u, which is equals to rho g delta v, that is mass times acceleration due to gravity, mgh, basically mgh2 minus h1. The change in kinetic energy is delta k, which is equals to rho delta v times v2 square minus v1 square. We can employ the work energy theorem to this volume of fluid. This yields P1 minus P2 delta V, where is the work done, which is equals to change in kinetic energy which is equals to half P delta V square V, which is equals to V square minus V21 square plus rho G delta V H2 minus H1. Now again we divide by delta V, which is common on all of these. We will get this equation. The pressure difference, which is equals to this. We can rearrange the above terms to obtain P1 plus this is equals to this one, and from this we can say, this is Bernoulli's equation, from this we can say that the sum of pressure and half of rho v1 square plus rho gh will be constant. Since 1 and 2 refer to any locations along the pipeline, we may write the expression in general where this is equals to constant. In words, the Bernoulli's relation may be stated as follows: as we move along a streamline, a sum of pressure P, the kinetic energy per unit volume, and the potential energy per unit volume remains a constant. Note that apply the energy conservation principle. There is an assumption that no energy is lost during friction, but in fact, when fluids flow, some energy does get lost due to internal friction. This arises due to the fact that in a fluid flow, the different layer of fluids flow at different velocities, these layers exert frictional forces on each other, resulting in a loss of energy. This property of fluid is called as viscosity and discussed in more detail in a later section. The lost kinetic energy of fluid gets converted into heat energy. Thus, Bernoulli's equation ideally applies to fluids with zero viscosity or non-viscous fluids. Another restriction on the application of Bernoulli theorem is that fluids must be incompressible, as the elastic energy of fluid is also not taken into consideration. In practice, it has a large number of useful applications and has explained a wide variety of phenomena for low viscosity incompressible fluids. Bernoulli's equation also does not hold for non-steady or turbulent flows, because in that situation velocity and pressure are constantly fluctuating in time. When a fluid is at rest, its velocity is zero. Bernoulli's equation becomes, where kinetic energy will vanish, only potential energy will be there, where P1 plus rho g h1, which is equals to P2 plus rho g h2, where this difference between pressure, which is equals to rho g times difference in height, which is basically kind of formula rho g h formula. What is the main thing in Bernoulli's equation? Basically considering the work done here, which is equals to P1 delta V from P1A1 times V1 delta T. That is the equation that we converted into P1 delta V since volume is constant. And W2, which is equals to same thing, P2 delta V. And total work done, we just subtract the two. Final minus initial or initial minus final. Depending on that, we will get the work done in the fluid. And considering density, we will get mass of the fluid is again constant, which is equals to rho A1 V1 delta T, where V is velocity, A is area, delta T is time, which again we will get, from which we will get mass to be rho delta V. It is the mass passing through the pipe in time delta T. Basically, for continuity, equation of continuity, we only needed to use this relation. We got everything. But in Bernoulli's equation, we also need the work done, which is work done equations along with this relation, and we equate it to change in potential energy, which we get mass times g times change in height, and kinetic energy, which is half into mass times v square, which we take it as difference between the velocities. There must be a half here. And work energy theorem, which basically states that Work done, which is equals to change in kinetic energy. Work done we got in prior equation. We got P1 minus P2 delta V. Okay, they use not work energy theorem but work energy principle. That is conservation of energy. It includes potential energy. Because of that, we take a sum of change in kinetic energy by and in sum of work change in kinetic energy and change in potential energy. Let's check that once again. Change in work done by all forces on the object. We will get this equation from that. Work done we got because of the prior equation. This we will get from the work energy principle. Now, since delta V is common, we cancel it out. We will get the Bernoulli's equation, or by replacing or rearranging them, we will get that P plus half rho V square plus rho GH, which is equals to constant. We can try to derive it ourselves. Let's do it. If we take a pipe of varying area at different heights, H1, H2, from the ground of area A1 and A2, velocity this way. Now this, if we consider this distance to be v delta t, which we got from velocity, which is equals to distance per time, and the distance, which is equals to v delta t, if we consider as v1 delta t for the small distance covered. Here we take it as v2 delta t. Now the first thing we do, and there is pressures P1, P2 at these two areas. Now the first thing we do is find work done, which is At first surface at this region, we will find out v1 which is equals to force 1 into displacement or distance, which is equals to force 1 which is equals to mass into, we don't need that, we can use pressure formula, not mass into acceleration. Force which is equals to P, P1A, because pressure which is equals to force by area, we will get F1 which is equals to P1A times displacement V delta T, work done 1 which is equals to P1A into V delta T, where this is velocity. Yeah, this is velocity, and we can write area into velocity, we can write as x by delta t again, delta t cancel, area into distance which is equals to volume, so work done which is equals to P1 delta V, work done 1 which is equals to P1 delta V, work done 2 similarly at second surface which is equals to P2 delta V. Now total work done which is equals to V1 minus V2 which is equals to P1 minus P2 times delta V. This is the work done. That became an oval, should not be an oval. Okay, then yes, so now we use work energy principle. No, not work energy, it was, yes, it's work energy principle. Work energy principle, which states that delta W which is equals to delta K plus delta U. But we still did not find delta K and delta U. Let's find that out. Ke or delta K which is equals to, or delta, let's find K1 first. K1 kinetic energy at position 1 which is equals to half mv1 square. Now mass which is equals to rho v or rho delta v. Density, let's just write this Ke1 which is equals to half rho delta v, which is in place of mass, v1 square, Ke2 which is equals to half rho delta v, both are constant, v2 square. Now delta Ke or delta K which is equals to K2 minus K1 which is equals to, or K1 minus K2 which is equals to, or the common things we take out, half rho delta V which is equals to times V1 square minus V2 square. This is change in kinetic energy. Now because at variable height there is also change in potential energy. Now change in potential energy, we should find out actual potential energy which is equals to mgh, mg delta h we can take. Based on that mass value we know, mass which is equals to rho delta v. Now substituting value, v u delta u is equals to u1 minus u2 is equals to rho delta V common, G common, H2 or H1 minus H2. This is the formula for change in potential energy. That's a unequal shape. Let's redraw that. That became an oval. Why is it becoming an oval? It was clearly a rectangle. Okay, good. This is a change in potential energy. Now we come back to the work energy principle, which states that delta V is equals to delta K plus delta U. Substituting everything in the delta W, which is, and we also have delta W, which is here P1 minus P2 delta V, which we got from using just force formula, force into displacement formula, and pressure formula, where P1 minus P2 delta V, which is delta work done, is equals to kinetic energy formula, half of rho delta V, rho delta V times V2 square minus V1 square, or V1 square minus V2 square, plus rho delta Vg H1 minus H2. Now the common one is delta V, delta V, delta V cancel. We will get P1, this is delta K, delta U. Work energy principle, P1 minus P2, which is equals to half rho V2 V2 square minus V1 square, whatever it might be. I'd rather prefer to write it as delta V square, but let's just write it right now. Rho G H1 minus H2 or H2 minus H1. It's not right to shift them without knowing the values. It is based on the values right now. These values, these position values, it's actually wrong equation. So it's better to write the correct equation. And we have delta V1, which is P1 minus P2. So this now should be correct. Where let's erase this and write it again. P1, P2. Now it's correct equation. This is a part of the pre-completely condensed, or let's just say it's just a preview of the equation, which we will get a new equation from shifting it and rearranging it. Let's split the terms. P1 minus P2, which is equals to half rho V1 square minus half rho V2 square. I think we should write this as P2 minus P1. Yeah. Now it might be correct. Yeah, now it should be correct. Plus rho GH1 minus rho GH2, where we send all the negative signs to the other side, we will get P2 plus half rho V1 square plus rho GH2, which is equals to half rho V1 square plus rho GH1 plus P. P1. P1 got sent that side. This is the complete Bernoulli's equation. Okay. Complete Bernoulli's equation. Bernoulli's derivation. And based on this, since there are two different values equal at two different positions. Okay, this is supposed to be two. Any two different positions of the pipe, so we can consider P plus half rho V square plus rho GH to be constant, and we can derive two forms from of this equation. That is, if water at rest, no flow, then V, which is equals to 0. So P plus 0 plus rho GH is equals to constant. Or basically, using this equation we can get it. Let's use that equation itself, not this one. Where we will get P2 minus P1, which is equals to kinetic energy is 0, 0 plus rho G, this is rho G H1 minus H2, I believe. Yeah, that's the case. Now P2 minus P1, which is equals to rho G H1 minus H2. This equation is very similar or same as the one which we derived from the cylinder or water suspended in a container one, where we got P2 minus P1, which is equals to rho GH. We are just finding the actual height through a difference of height. So basically a same equation. I believe we can find one more form of this equation here, that is Bernoulli's equation. From here we can find one more form of the equation, that is by taking that the pipe is at horizontal. Basically the pipe is straight. There is no difference in height. If we take, there is no potential difference, basically delta H, which is equals to 0, or H2 minus H1 equals 0. In this condition, if we find out the Bernoulli's whatever that is, P2 minus P1, which is equals to kinetic energy half rho V2 minus V2, no wait, it's V1 square minus V2 square plus rho G H2 minus H1, which is 0. Basically a horizontal pipe. In this case, both this height is same, or any kind, any place it is same. So H2 minus H1 is 0, whole term will become 0, delta U equals 0. In such a case, P2 minus P1, which is equals to half rho V1 square minus V2 square. This is the one more form. Or we can say that P plus the half rho V square, which is equals to constant. Pressure plus half rho V square, which is equals to constant. Or whatever, a special way to call this is by calling it as kinetic energy per unit volume, because rho, which is equals to mass by volume, so we can basically multiply it with volume. This will become kinetic energy times volume, which is basically kinetic energy for unit volume of water. Okay, that is about Bernoulli's equation. Let's go back. Now, there is, before going to the next topic, that is speed of efflux, Torricelli's law. Let's see something about Daniel Bernoulli, the great scientist who gave our Bernoulli's equation. Daniel Bernoulli. Daniel Bernoulli from 1700 to 1782 was a Swiss scientist and mathematician who, along with Leonard Euler, had the distinction of winning the French Academy Prize for Mathematics 10 times. He also studied medicine and served as a professor of anatomy and botany for a while at Basel, Switzerland. His most well known work was in hydrodynamics, a subject he developed from a single principle, the conservation of energy. His work included calculus, probability, the theory of vibrating strings, and applied mathematics. He has been called the founder of mathematical physics. That's about Daniel Bernoulli. Now let's go to the next topic, that is speed of efflux. Speed of efflux, Torricelli's law. The word efflux means fluid outflow. Torricella discovered what the speed of efflux from an open tank is to. This Torricelli is the also the person who performed the who first gave the way to measure atmospheric pressure. The mercury barometer experiment was also performed by him. Just a reminder. Torricelli. Okay, the word efflux means fluid outflow. What efflux means is that it is the outflow of fluid. Torricelli discovered the speed of efflux from an open tank is given by a formula identical to that of a freely falling body. If we consider a tank containing a fluid of density rho with small hole in its side at height h, at height y1 from the bottom, the air above the liquid whose surface is at height y2 is at pressure P or P2 from the surface. From the equation of continuity, we have V1 A1, which is equals to V2 A2. Torricelli's law, the speed of a flux VL from the side of container is given by application of Bernoulli's equation. If the container is open at top, then V1, which is equals to rho 2 GH. Basically, this is a container. This is a container containing water till this level, and the height of the water is given as y2. Height of the water is given as y2, and there is a hole at the side of the container through which water is going out like this, and this water has a velocity called the, I think it is given here somewhere, speed of efflux. The water has a velocity called the speed of efflux. The velocity is speed of efflux and is denoted here by VL. This is not VR, this is VL. VL is the speed of a flux of the water here. And okay, first thing here, this is the height of the water. Total height of the water is represented by Y2. Now there is a hole at the side of the container. It is at a height Y1 from the depth of the container, and this H represents the height of the water above the hole. And A1 denotes the area of the hole, A2 denotes the area of the container, P2 denotes the pressure, PA denotes the pressure at the hole. Okay. If we assume the cross-sectional area of the tank is A2, what I said is much larger than that of the area of the hole, A2 is much greater than A1, then we may take the fluid to be approximately at rest at the top, that is V2 equals 0. Now applying Bernoulli equation at points 1 and 2 and noting that at hole P1 is equal to PA, atmospheric pressure we have from equation 10.12, which is equals to PA plus half rho V1 square plus rho GY1, which is equals to P rho GY2. One we will take, before going on, we will take a 10-minute break. I'll be stopping the stream. It is not a 10-minute break, but good night.